Welcome, my name is Itai Segev. I'm a senior kernel developer here at Wolfram Research, and I wear multiple hats in the company. Today I'm wearing my hat as a member of the mathematical and symbolic computation team, and I will be telling you about applications of symbolic arrays. So Adam gave an introduction to symbolic arrays and their calculus just before lunch. I will, if you've seen that talk, that will certainly help, but I'm not going to assume that you went to that talk, so I will sort of review things as needed throughout. But I'm going to introduce the functions array expand and array simplify through a survey of matrix and other identities. Then I will show how these can be used to solve problems people report on Stack Exchange. Then do a quick review of symbolic array calculus, and then I'll combine all these pieces into detailed examples, least squares and Taylor approximation. And you might think, Taylor approximation, why does that need a detailed example? Which is exactly what I thought until I started getting into the writing this talk, and then I was like, there's a lot here. It's worth taking this step by step. So let's dive right into it. Many key identities of linear algebra can now be proven and or applied using array expand and array simplify, or they're tied into simplify and full simplify. Array expand generally makes things bigger. Array simplify generally more compact. Of course, these are general rules. If you know that if you simple, and this is similar to expand and simplify. Of course, these are general rules because, if you manage to write 0 very cleverly and then you expand out and all the terms cancel, you might end up with just 0, which is very compact. And we'll see some things like that throughout this talk. So I'm going to begin by defining two n by n matrices. So we use the new in 14.1 function MatrixSymbol. We give it a typeset name, right? This argument, I could have used a graphics or a smiley face, but I'm being conservative and just giving it a letter name. That's how it'll be displayed. And then I'm going to declare that it's n by n. And we're gonna, I'm going to save these things in two symbols called a and b, just so I don't need to type these big expressions all the time. And so I'll go ahead and reevaluate that. And we start off with doing some basic identities. So the definition of an inverse A dot A is equal to A dot A inverse, which is an identity matrix. So this is symbolic identity array. It takes a list of dimensions and then gives an array with twice that rank, which is the identity operator in each of those dimensions. So if you give it just one dimension, it'll be the identity matrix, and voila, you get true, as you should. Now you can array expand the inverse of a product, and that gives you a product of the inverses in the opposite order. And if you do, you can then recombine those using array simplify. The conjugate is involutive. If you do it twice, you get back to where you started, at least if you only believe in finite dimensional matrices. If you can take a couple of the conjugate of a couple of matrices and expand it out, and then you can recombine them using array simplify, and they get reversed. And inverse and conjugate transpose commute, so you set them equal to each other, you ask for the array simplify, and boom, you get true. So now I'll give some identities with matrices and scalars. So here I'm going to declare k to be a complex number. The reason I need to do that is that array expand and array simplify, they deal with general arrays. So they can't just assume that unknown things are numbers. If you want it to be a number, you need to tell it that it's a real or a complex number, etc. So if you multiply a matrix by a scalar multiple and take the trace, you get the multiple, you get the trace multiplied by that scalar. You can pull out a scalar multiple through a power, and you get the scalar raised to that power. If you take the determinant of k times a, you'll get k to the n. Remember, these are n by n matrices. That's where that n comes from. The determinant of the inverse is the reciprocal of the determinant. And here we have that the determinant of the conjugate transpose is the conjugate of the determinant, which is really two identities at one, right? It's the determinant of the transpose is equal to the determinant, and then if you conjugate all of the entries, the determinant itself is conjugated. And a more advanced but still very neat identity, if you take the determinant of the matrix exponential of A, well, that's just the exponential of the trace of A. So some identities with similar matrices. If the similar matrices have the same determinant, and I do the same identity with the matrices in the opposite order and using array simplify. So, and this is one of those cases where array expand and array simplify both and do the same thing for us. Similar matrices also have the same trace. This last one is perhaps not strictly speaking a similarity identity, but it's proved using one. So matrix exponential gives you a representation of the additive group. You can you can break up the matrix exponential of s plus t times a into matrix of SA dotted with matrix of TA. So that's some matrix identities. Now these can, they're called array simplify and array expand, so they can deal with vectors and they can deal with arrays. Interesting array identities tend to be relatively complicated, so I'm just going to sort of show those as needed. But let's do some vector identities. So I'm going to define a couple of vectors. It's very similar. I have VectorSymbol. I give it a typeset name, and I give it a dimension, and voila. And there are my two vectors. So unlike dots of matrices, dots of vectors is commutative. And here's the definition of a matrix, of the transpose of a matrix or linear operator. If you have v dot a dot w, you can reverse the w and the v. Sorry about that. I will try to make my phone shut up. If I can. Sorry about that. I guess we're full of technical difficulties today. So definition of a transpose. If you have v dot a dot w, you can reverse w and v at the cost of transposing t. At the cost of transposing a. That's true. Now, a vector, of course, is its own transpose, at least in Mathematica. And a vector is orthogonal to a cross product involving it. Now, note that this implicitly made an assumption, namely that n is equal to 3. This assumption is made explicit if you just simplify the cross product of a vector with itself. Why is that? Well, these functions assume that their arguments are well defined. So we didn't tell it that n is not equal to 3. And so it's like, well, since this is a cross product of two vectors, you must be in 3 dimensions. And so n must be equal to 3. And we see that in this result. Now, going a bit fancy, we can try this again, only this time we're going to say that our vectors, rather than being n-dimensional, are 4-dimensional. Well, then it doesn't do anything because it's like, well, I don't know what to do with this. It doesn't even make sense. Now, if you give it the correct 4D variant, which is you need to have the cross product of 3 vectors, and in n dimensions, you need to take the cross product of n-1 vectors. Well, this does simplify. Of course, since I didn't define a third vector, even the term that's in parentheses is 0, and that correctly simplifies to the 0 vector in 4 dimensions. So that's some basic identities. And, this talk is talking about applications, and, some may quibble about whether or not what I've just shown you are applications, but an application is something that can help someone solve a problem. So I went to mathematics, not Mathematica, but Mathematics Stack Exchange, and searched for matrix algebra and a linear algebra function. And there were a lot of sort of super abstract problems, like how do I prove that this is the complete set of representations of this matrix algebra, which is not really a question we can actually ask, or they were super concrete, like I have this matrix, and how can I determine what this particular I have one unknown entry. Well, that's not really treating the matrix as a symbolic thing. So here are the first 3 problems I found that are sort of make sense, not too abstract, not too concrete, to be applied to symbolic matrices and arrays. And here's how we can solve them using our new functionality. So here's sort of a famous identity, a complicated way of writing A plus B. Well, that's really easy. We just literally type in both sides. It's very natural. We already have the 2 matrices. So we put that in, we get true. Then the next was to compute the transpose of this particular expression involving a covariance matrix and a one vector of ones. Whoops. And so what's the key property of a covariance matrix? It's that it's real and symmetric. And so reals. Right, so the elements are members of the reals set, and we're symmetric in the two dimensions of the matrix. So ArraySimplify knows how to simplify the transpose. The transpose is equal to the original matrix. Then the identity is easy. We just type it in, and ArraySimplify gives us the correct answer. Finally, let's show that if you recenter a vector and compute its squared norm, then that's equal to V transpose MV, where M is the identity matrix minus 1 over n, the outer product of 2 vectors of ones. So first, let's give a name to this, Vi minus V here, the recentered vector. So there's V. I've computed the average here. I suppose had I been more clever, I could have just written a total of V here rather than dotting V into the array vector of all ones, but it still works. And of course, we need to take the scalar and turn it into a vector with identical components. So we multiply it by the symbolic ones array. So there's our vector. Notice that the outer product of one array with itself is just the matrix of all ones. So we'll make our first attempt here just using ArraySimplify. And well, it does a little something, or it certainly transformed the input, but it doesn't get us very far. So I was hoping Simplify will get us all the way there. It doesn't. We know what the problem is, and so this should be fixed before we release. So hopefully by the time 14.2 is out, this will give true. It doesn't in my version of Mathematica today, but we can use component expand to verify this as any fixed dimension. So I'll just say that n is equal to 10, and I will do component expand, and then I'll expand out that product, and I get 0. And just for definiteness, what component expand does is it takes an expression and replaces all the arrays with sort of indexed components. And I need to choose a finite dimension because it can't write out n components for us. So here I'll just do it in n equals 2. And so you can see all the v's have been replaced with v1 and v2. And we multiply this out. And then if we were to expand this product, we would get 0. So I think I've been going for about 13 minutes. So I think I'm sort of right on time. Let's do a calculus review. Excuse me. So D can now differentiate with respect to symbolic array variables. For symbolic vectors, this is the familiar gradient, and grad can be used in the same manner. For higher rank arrays, this is a generalized gradient, and in general, if you have a rank k, you differentiate a rank k array with respect to an array of rank L, you'll get an array of rank k plus L. And so I'm going to illustrate this with various examples. So I'm going to define some variables. And since I now have vectors, matrices, and arrays, I'm going to rename my matrix M. And I'm going to use A to represent my array, which is n by n by n. So starting with the world's easiest example, let's take the gradient of a scalar with respect to a vector. Well, we get a 0 vector in dimension n. We can do the same computation with grad. Beautiful. Now we can do this calculation with take the derivative of 5 with respect to a matrix, and we get a matrix of zeros, the n by n, matching what M did here. So now let's take a constant array in k dimensions and differentiate it with respect to M. And we get a 0 array out. Notice that, the new dimensions come at the end, as is the way D has behaved since version 1, or at least since version 6, when it learned how to do these array derivatives. And so we get k and n as the dimensions of our 0 array. Now, the derivative of an array with respect to itself is always an identity array of the appropriate shape. So D of V with respect to V is the identity matrix. Of M with respect to M is a rank 4, n by n by n by n identity matrix. And A with respect to A gives us array 6 identity array. Let's differentiate a quadratic form with respect to a vector. Sort of familiar product rule, m dot v plus v dot m. We can do the same thing with a vector valued quadratic form. We get basically the same result, only we need to write it a little differently in order to get all the indices to line up. Let's differentiate with respect to the array on the inside. That's, we get this new notation for transpose :2, which says slide all the indices over by 2. So basically we dot in the last slot and then we move everything over by 2 and dot in. So we're basically making sure the slots line up correctly. I'll have a more concrete example of that later. And let's just confirm my claim that the rank of the derivative is the sum of the ranks. Well, we had our input had rank 2, our differentiation variable had rank 3, the result has tensor rank 5, 2 plus 3 is equal to 5. Great. So many functions have built-in rules, like the determinant, the derivative of the determinant with respect to the input matrix is the, excuse me, is the transpose of the adjugate matrix. And of course, we have an appropriate chain rule. So here I'm taking the derivative of v dot a, right? So that's, I've taken away one slot, so v dot a is a matrix. And so we have the same thing. And then we have, another v dotted into an identity array. And then we have this new array dot, which means take the last two slots of this array and dot them into the first two corresponding slots of this array. We're going to see array dot again in the future. So higher derivatives are supported. So here's the second derivative of v dot v. That's twice the identity matrix. Great. And div and Laplacian, there are some issues, which maybe I'll have a bit of time to talk about, but they do work, at least in some cases. So there's the divergence of v with respect to v, and Laplacian of v dot v is 2m. Okay. All right, so with all those pieces, let's talk about least squares. So what's least squares? Least squares is given the matrix A and a vector B, we want to find the best solution to AX equals B, i.e. the X that minimizes the norm of AX minus B. So we're going to define some variables, and interestingly, oh, I know what the issue is. I need to clear M here. And so I'm going to define A, B, and X. So A does not have to be a square matrix. So I have here an n by m matrix. And I'm going to declare it over the reals because I'm going to want to differentiate the norm. And if it was complex, then we'd have conjugates and it wouldn't be differentiable. So we want to minimize this norm. I'll minimize the norm squared just to make it look more pretty. That's the same thing. So we take the expression we want to minimize and we differentiate it. In order to have a minimum, we first must be at a critical point. This may not look like the standard expression you see in textbooks, but it is, as we can verify using simplify. And if you think about it, right, we just need to move this A to the other side. And what does that cost us? That costs us a transpose. Okay, then sort of the way one would proceed from here is you'd say, well, let's assume that A transpose A has full rank. Well, then it has an inverse. And so we can say that X is A transpose A inverse dot A dot B, which is the pseudo inverse of A. So first of all, for there to be an inverse, A transpose A has to be full rank because it's a square matrix. And the pseudo inverse, for this to be equal to the pseudo inverse, that has to be full rank. So we've made a couple of assumptions here. Well, how do we know we can do that? Well, in order to guarantee that we're at a minimum, the second derivative must be positive definite. Well, what's the second derivative? It's that. Let's simplify that. Well, that's twice A transpose A. If that's positive definite, that means A transpose A has no zero eigenvalue, i.e. it's invertible, i.e. all the steps we took above to find the solution are in fact valid. So yay, least squares works. A century of mathematics is not wrong. Excellent. Okay, so I'm going to, and how am I doing on time? I have about, yeah, it looks like I'm sort of right on time. That's good. Taylor approximation. We're going to use Taylor approximation to approximate a scalar value function of matrices. And, you know, these are going to be expressed in terms of a base point m and a displacement delta m. And I'm just going to sort of, you know, create these two matrices right here, which I will then use. All right, so the first piece is really quite simple. You want to define a function. So there's f of m. It's picked a simple function, determinant of m. Now, let's compute the first derivative. You know, normally when I do this sort of thing, I just say, you know, d1 of m is equal, well, I might do just, you know, d equals f prime of m, or I might say d1 of m is equal to d of f of m comma m. But there's a problem with that here, right? If we just had a symbol m, it would d would assume, oh, this is a scalar variable, so I'm going to take the scalar derivative. I'm going to take the determinant of a scalar, which I don't know what that means, and then I'm going to differentiate it. Well, what do I do with that? So you need to compute this expression using an array, a matrix variable. So I have here the m from up here that I copied and pasted into here to get the correct shape. And then I replace that matrix symbol with just the normal symbol m. Why do I do this replacement back to m? Well, if I didn't, I would have a literal copy of the matrix m inside of the result, which would sort of defeat the purpose of having defined the variable here to begin with. So this is a little bit uncomfortable. I don't know that we have a great answer. Adam and I both encountered this in different ways and sort of came up with our own solutions. But that's sort of the way to do it. Now that we know what the trick is, computing the second derivative is straightforward. This is kind of an ugly looking thing. I suppose I could simplify it probably a little bit, but I like to think of this as the following. Right, you have the determinant, then you have, what is this thing doing? Well, we're dotting m into the last slot of, m inverse into the last slot of this rank 4 array. Then we're sliding everything over by 2 and dotting the last index of m inverse into the first slot of the result. And so here, I write this out sort of as the matrix product, m inverse, and then there's the identity array. And so the first slot of m is 5 in here, and then the second slot of the first m inverse is 2. The first slot of this m inverse is 3, and that goes into 6. Because we started by putting it into the last slot and then we moved it 2 over. The other simplification we can make is m inverse times this tensor product with scalar multiple of n inverse times this ones array. Well, that's just taking the tensor product with m inverse. So there's a simplification. And this is one of those infinite number of identities that we can't quite do yet. But if we were to do this using component expand, we can verify that this is true. Went down to n equals 4 and 10 instead of n equals 10 because we have a rank 8 tensor here. So the number of components grows quite quickly. I don't recommend expanding this out into 10 million, 100 million components. All right, so now that we have the derivatives, it's easy to define the polynomials. The first one is pretty trivial, right? It's just the function. Then for the second one, well, we're going to, sort of follow the rule. We're going to have f plus d1, the first derivative, and it's array dotted with delta m, right? Because we need to contract. This is a rank 2. This is a matrix, so we need to end up with a scalar. So we contract all the slots of the derivative with the matrix. Another way to think of it, a way that's easier for me to think of this is, right, we took the tensor product of the derivative with delta m, then we contracted the corresponding slots. So that's that. Then similarly for the rank 2, we have a 1/2, and then we're going to have 2 array dots because the second derivative has rank 4, so we need to dot in 2 copies of delta m in order to contract all the slots. Even though conceptually this could have been written using tensor contract, in practice it can't because there's this non-tensorial multiplication of m inverse by the ones array. So tensor contract would be unhappy if you tried to use it here. The other, there's the derivative. It's kind of ugly looking, but it is what it is. And I'll just point out that we could have written this in the sort of more symmetric looking form, delta m dot m dot delta m, as we can verify using simplify. Notice that this identity only holds for square matrices because, you know, that's the only way all the slots line up. And so, you know, the array simplify is doing real work here. So now that we have our polynomials, let's try them out. We'll generate a matrix of random integers and then a perturbation, which has entries that are roughly 100 times smaller. So I will generate these and I will look at the exact result. I mean, the exact result is a rational with a very large denominator, like 60 digits, so we'll just look at the numerical approximation. The 0th order approximation is not too bad. Of course, it's just equal to the function at a. First order approximation gets us quite a bit of the way towards where we want to be. And the second order approximation gets us 3 or 4 digits. In this case, we get 60637 as compared to 66039. So yeah, we got 4 digits out of this. Just to explain this, why do I have this strange block here? Well, right, my derivative here has literal values of n in the ones array here. And in the identity array. So we need to give, say, well, it's a ones array of the correct dimension. And this normal expands out the symbolic ones array and symbolic identity arrays into explicit arrays so we can finish the computation. So that is Taylor approximation. You thought it was simple, but it has tentacles. So in conclusion, 14.1 gave us symbolic arrays, including vectors and matrices that we could compute with. In version 14.2, we have new functions that allow us to manipulate them symbolically, much as version 1 allowed manipulation of elementary algebraic expressions. So 14.1 was, if you will, the MATLAB of symbolic arrays, and 14.2 is now the version 1 Mathematica of symbolic arrays. So a much wider array of problems can now be tackled. I want to thank the rest of the mathematical computation team, especially Adam, who did most of the heavy lifting, and you know, responded to my bug reports as I was writing this talk, fixing some of them before today, and promising to fix more of them for release. And with that, I will see if there are any questions. Yes, I've been asked if I can share the notebook. I was told that for some reason the talk couldn't be updated until after I gave it. So I will be sending in the notebook and it will be downloadable shortly. Right, so there's, so one question, the first question I see here is, I said a vector is its own transpose, at least in Mathematica. Can you please explain the rest of that thought? Why did you add in Mathematica? So the reason I said that is that in many textbooks we sort of differentiate between row vectors and column vectors, and then a transpose is converts a row vector to a column vector. So it, a vector, there isn't such, or I suppose even in something like, say, MATLAB, right? There isn't such a thing as a vector. There are n by 1 matrices and 1 by n matrices, which is sort of very in keeping with a certain strand of teaching linear algebra. And so, and therefore, a row vector times a column vector is different from a column vector times a row vector. In Mathematica, a vector is a vector. It has rank 1. Doesn't matter whether you display it in a row or a column. And, you know, it's the same object, which is why some of our identities are more complicated than others. Is it possible to have a line-by-line proof that an equation holds instead of only getting true? In some cases, you can maybe get part of the way there. Like if you do array expand, you might get sort of one, you know, sort of like we saw with the, you know, with like the product of the, you know, expanding the inverse of the product, right? So maybe you can do them, but in general, you know, what our functions allow is sort of verification. They're not sort of proof generators. That's sort of a different thing. Is it possible to discover formulas? I don't think we have sort of anything automatic for that. You can certainly, you know, generate things and try them out using, you know, component expand, say, but we don't have something. We don't have like just like we have like a find, you know, find sequence, I think it's called, right? You give it a bunch of numbers and it tries to come up with a formula for it. We don't have something like that for you give it a bunch of matrices and it tries to give you a formula for them. I'm not sure if something like that is even generally known in the literature. That sounds like a pretty hard problem. Can you please provide a short and sweet explanation of what is different special about the new symbolic vectors in 14.1, 14.2? What is the essence of what has changed and the new improvements? I would say that there are two key differences. One is that, so previously you could do these many of these same calculations, and in fact, I gave a Wolfram U new in 14.1 webinar on this feature, and I pointed out you could do many of these things using assumptions. So you could make an assumption, A is an element of matrices NN, and then do stuff with that. By sort of packaging this up into a self-contained object, then many functions that don't accept assumptions, like you know, D, can now exploit the same information. And the other key advance was the non-threadable attribute, which Adam talked about in his talk, which allows you to combine symbolic arrays with explicit arrays without Mathematica's automatic threading behavior ruining the structure. So if you want more details on that, I recommend you take a look at Adam's session from 11:30. I presume the slides are there, and the recording will be available. Is there a way to get Mathematica to print out all assumptions that are being made during function execution? In general, no. I don't know if Adam is here in the session and if he can contribute a partial answer to that. I'm not aware of anything you can do like that. So I'll say the short answer is no. Okay, and I think I believe that's right. Yeah. So I see a question about notebook download. Like I said, I will be posting it. It just, I was told that for some reason it couldn't be done until after my talk. So I'm going to fix the couple of typos I found while giving this talk and then send that in to the events team. And so I imagine later this afternoon, the slides will be available. So I will now pause for another, say 30 seconds and see if anybody wants to contribute another question. Okay, Q&A chat is closed, so there will be no more questions. So thank you very much for your time, and I hope you have enjoyed this talk and the rest of the conference. Bye.